41 from chapter 35. Chapter 35, problem 41. If nobody wants to read it, just give me the book and I'll read it.
A good grading cut in a something metal has 5,900 lines per centimeter. If this grating is illuminated with white light ranging over wavelengths from 400 nanometers to 700 nanometers, it will produce a spectrum ranging over some interval of angles. From what angle to what angle does the first order spectrum extend?
Okay, so we have this grating that has 5,900 lines per centimeter, and we're shining light that has a wavelength between 400 and 700 nanometers. That is the visible range. 400 nanometers is basically purple, 700 is basically red. So those are all the colors that you can see. And we're going to shine this light, and each of these light wavelengths is going to be diffracted a little bit differently. Okay? And you're going to calculate the angles of those diffraction. What is the equation that we use for diffraction or interference? There's one equation. M lambda equals d sine theta. Okay. So I need to know what are the variables in all of this. In part A, they want the first order bright spot. So where does that come into play? First order, what does that mean? It's not Star Wars villain.
The second light spot?
First order bright spot is
Zero.
m equals 1.
I thought it was
The
M
central
equals
bright
0.
spot is m equals 0.
Oh, okay.
The first order is m equals 1. Lambda is the wavelength. We're going to calculate the angle of diffraction that we get for both 400 and 700 nanometers. So we're going to do it twice for each part of the problem to get the range of angles that we're diffracting. D is the line separation in your grating. It's how many centimeters are between the lines. So do we have D? Is D equal to 5,900 lines per centimeter?
No.
1 divided by this gives you D. Okay? That is the trickiest part of this problem. D equals 1 over 5,900 lines per centimeter. So if you do that division, you will get a number. You will get 1.7 times 10 to the negative 4. What are the units of that number?
Centimeters?
That gives us number of centimeters, basically centimeters per line. What do I want to probably convert that number into? Convert that into meters. Get everything into SI system. So we get that's equal to 1.7 times 10 to the negative 6 meters. We're asked to find the angle that the diffraction happens. What are the ranges of angles? So we want to solve this equation here for the angle theta. So we're going to get theta by itself. Yep. So I could do that by divide both sides by d. M lambda over d equals sine of theta. How do I then get theta by itself? Take the inverse sine. Theta is equal to the inverse sine of m lambda over d. So that's going to be the key equation that you're going to use in every single part of this problem. This is the same as saying arc sine of m lambda over d. Okay? Questions on that process? So now for the range of angles for the first order, we would plug in our angles, or plug in our wavelengths. So for the first order, theta for 400 nanometers. I'd plug in sine inverse m equals 1 because it's the first order times 400 times 10 to the negative 7 meters. 400 times 10 to the negative 9, sorry. Divided by 1.7 times 10 to the negative 6 meters. Plug this in, I got 13.7.
Where's the 400 coming from again?
400 times 10 to the negative, 7. They give us 9, yeah, negative 9 meters. The 400 is the wavelength. So they gave you a range of wavelengths. They said between 400 and 700. So we're plugging in the small wavelength first, and we plug all this in, plug it into your calculator, you get 13.7 degrees. Do the same thing, theta 700, inverse sine, 1 times 700 times 10 to the negative 9 meters divided by 1.7 times 10 to the negative 6. And we get 24 degrees. So that's the range of angles that we get between 400 and 700 nanometers for the first order bright spot. How would I do that? Yes?
So, 400 is that negative 9 or negative 7?
Negative 9.
Okay.
Nanometers. Nanometer is 10 to the negative 9. Yeah, right. Because it's nanometers, nano is 10 to the negative 9. So it's just the metric conversion. Second bright spot, how would I do that? Just put a 2 in for m. Theta 400 equals inverse sine of 2 times 400 times 10 to the negative 9 divided by 1.7 times 10 to the negative 6. Plug and chug your numbers in. You got 28 degrees. Same thing for 700. Just plug in a 2, you'll get about 56 degrees. Third bright spot. What do I do differently for the third bright spot?
Put in 3.
Plug into 3. M equals 3. Plug in 3, you got theta 400 nanometers is 45.1. Theta 700, if you plug that into a calculator, you get a big fat in-def. Depending on the calculator you're using. What does that mean?
I don't know.
Mean you plugged into your calculator wrong?
No. You gave it.
So the way this picture works. So this angle that you're getting is this angle right here. Yep. What's the maximum amount that that angle can diffract? Can we figure that out? This angle can get bigger, right? I can keep getting bigger and bigger. Biggest I can get is 90. So when you plug in these numbers for m equals 3, you end up with an angle that's greater than 90. So you're not going to get a result. Okay? So that means that this third order won't be complete. I can't get a complete third order. You're late. You have no seat. I shouldn't let you in. But you can come in. Okay? So because this is indefinite, because this will not give you an answer when you plug it into your calculator, that means the third order is incomplete. It means that light would be diffracted more than 90 degrees, so you won't get the third order. Here, come over here, James.
What is it trying to do?
Sharpen a pencil. They wisely installed the pencil sharpener where it's not useful.
James, you're the only person that ever
Our button is inside the
pencil.
pencil sharpener.
Since like elementary school, I haven't seen
Okay, so the third order is incomplete. One other question. It asked one other question. It asked if there's any overlap. Is there any overlap between these orders? You say yes? Amit says yes. Leah says no. Is there overlap? How do I know there's overlap? Between the second and third. The second and third, 400 is diffracted 28 degrees. 400 is diffracted 45 degrees in the third. So those don't overlap with each other. 700 nanometers, red light, is diffracted 56 degrees. Blue light, purple light, for the third order is diffracted 45 degrees. So the red light from the 700 from the second order is going to overlap with the blue light from the third order. So there is overlap.
How do you know it's overlap?
This angle is smaller than the one for the previous order. Okay, so what this would look like on this screen, the second order might look something like, let's see if I can draw this.
So if an angle from the higher order is lower than an angle from the lower order,
Then they overlap. So it would look something like, let's see if we can draw this. Something like the red might be diffracted 56 degrees. And some blue from the next one might be diffracted 45 degrees. So this is the third order. This is the second order. The second order is bleeding into the third order. Okay. Any questions on that one? That was the question from the homework. No? Yes, Leah.
So, that's only between the second and the third order.
That there's overlap. Is there any other overlap? We could look. Let's scroll up. So the first order is diffracted 13.7 degrees and 24 degrees. Then the second order starts at 28 degrees. That 28 degrees starts after the first order, right? After that 24 degrees. So there's no overlap there between the 24 and 28. Where are my fingers? Have my fingers made it all the way through?
Oh, yeah, they're right here.
Okay, let's do my finger pull before we move on to talking about the quiz. Remember, this affects the hand that we're going to make for an 80-year-old man in Virginia.
Oh, that's so cute.
Yeah, poor little guy. Insurance won't buy him one, so we're making him one. It's taken 2 years to get to this point. Who likes the soft finger more? Raise your hand. Soft. 1, 2. I mean, more natural, more realistic. 1, 2, 3, 4, 5, 6, 7. 7 of you.
May, did you feel them? Like what? Can you throw them at me so I'll feel them?
More statistics. You're going to spoil this man's hand. He's going to use this.
I think
He uses it, actually, he uses it for driving. He's an Uber driver.
He needs grits.
Okay?
Oh, Elijah.
6. How many like the not soft finger more?
Shouldn't he choose? Shouldn't the Uber driver choose? Why are we choosing for him?
All right, Nate doesn't matter.
Yeah,
Should it?
he never did.
Should the-
And then the tiebreaker. Dave, what do you think? Dave likes this up.
Good thing it mattered.
Maybe like 23.
Alright. There you go.
Finger not
Tell them
soft.
what your plan is.
So my plan doesn't really matter what you guys are going to say. We're gonna get something in between the hard and soft finger, so it's not super soft like the soft one, but not super rigid like the hard one. So it's kind of in between. We just wanted to do a poll and waste your time. So thanks for letting us do that.
Yeah.
Thank you.
Nicholas fingers.
Elijah needed something to do while he was eating his chips.
Sat in physics for that.
Yeah, yeah, right. They're pretty cool, right?
Yeah, I know
but
they
he
are.
should
Yeah.
get closer to the hard finger.
He did a
Yeah.
good job, right? This is neat. He came up with all this himself.
Like that?
I just 3D printed the mold.
It's true.
He's doing all the silicone, all the pouring, and he's putting like flocking powder to get the coloring right.
I'm a real chemist.
It's very cool. It's very cool.
I had a chemistry lab with you.
I know, I gave you my fucking report.
I copied your reports at one time.
I didn't hear any of that. I gotta report that.
No.
Yeah.
It's called group work. No, we were in the same group one week.
It's called cheating.
Now you know how Brooke gets an A in class.
We don't do that.
Yeah.
It's going on YouTube.
Bunch of cheaters. Yes, it is. It's all recorded.
It's fine. I got an A- and he got an A.
All right, million view hit. Come on, million views. Okay, so let's talk about the quiz questions now. So the very first quiz question was something about frequency. And what is the frequency of this thing going through water? Yeah. So you had this this question. You're given wavelength in air is 510 nanometers. And then you have the index of refraction in water of 1.32. And it wants to know what's the frequency inside of the water. It's kind of a trick question. Why is it a trick question?
It says 1.32 isn't used.
Frequency doesn't change inside of water.
Does frequencies change in air?
Frequency doesn't change in anything. So the frequency doesn't change. So do we need 1.32?
No, but why?
No, because the frequency doesn't change at all. If I needed a new wavelength, I could calculate the new wavelength. So I read this question and I kind of didn't think, because I'm high on Mucinex still, and I did, oh, the wavelength in the material, that's going to be, what would the wavelength of the material be? This is going back last chapter. Wavelength inside of a vacuum, inside of air, divided by n. So I can use the index of refraction there, and I can figure out what the wavelength becomes. But when you're traveling through a material, the speed of light changes. The speed that you're going gets slower. The speed of light is 3 times 10 to the 8th only inside of the vacuum. The speed of light changes. So that the frequency stays the same. So I just need to use this number, this wavelength, and calculate what its frequency is. Frequency equals c divided by lambda. Frequency, what is c? 3 times 10 to the 8th.
Meters per second.
Meters per second. Also a video game called Sea of Thieves, now available on Microsoft platforms. Monetize! Divide by the wavelength of 510 times 10 to the negative 9 meters. Speaking of waves, the wave physics in Sea of Thieves are very physically realistic. Another advertisement for Sea of Thieves, now available on Xbox. Frequency, if you do this division, is 5.78 times 10 to the 14 hertz. I don't remember which option that was, but that is the correct answer. And it was very well explained on the forums themselves too. So you can see an answer to this one. By an excellent physics student who has an excellent name. He just spells it wrong. Okay, so quiz question number 2. So number 2 was a diffraction, was an interference problem. So they give us a slit that has a width of 1.2 millimeters. They give us a wavelength of 60 nanometers, and they ask us what is the angle of interference, angle that we're diffracted by. We use the interference equation, m lambda equals d sine theta. They told us which bright spot it was. It was the first order bright spot. So we have m equals 1. We do our equation to solve for theta. Theta is the inverse sine of m times lambda divided by d. Theta is the inverse sine of 1 times 60 times 10 to the negative 9, all divided by d, which is 1.2
times 10 to the negative 3.
Yeah, so the negatives are the conversion factors.
Plug this all into your calculator. You might get this answer, 0.0005.
That was not one of the options. Did anybody get this?
No.
Try, take out your calculators. Try plugging it into your calculators. Well, this, I'm doing this on purpose.
I got it.
If you get this answer, that is in radians.
The answers that you were given were all in degrees. So if you take this number and you multiply it by 180 degrees divided by pi, you will get the answer that most of you hopefully got, 0.0286 degrees. Okay. If you get super, super, super tiny numbers, something like this for an angle, you're probably in radians, so check your calculator. If you get this number, you're in degrees, and that's where you want to be. Okay.
Thank you.
If you gave your answer as this first one, then it'd be fine as long as you attach the units to it, as long as you tell me that you know that that's radians. Okay? Questions on that one? No questions on number 2? Okay, number 4. So for some people, the slit separation wasn't showing.
Yeah, it was just M.
That's correct. Yeah.
Give us a unit. Do not believe it.
So for all the wonderful people listening on YouTube, I'm calling out my students for lying. They're all liars. Because this quiz question definitely has the slit width given.
No, it didn't.
No.
Physics 272,
It said width up and.
Yep.
And I did a lot.
quizzes,
And
Yeah.
it was.
chapter 35.
Here's just a
Definitely
little
rigged.
different. You made changes to this quiz. You're just trying to frame us.
Oh, oh.
Students have already taken. Be careful about making and not making any changes yet, because it constantly warns me. I go down to question number 4, and I see the second angular minimum location for a single slit diffraction having slit width of blah and wavelength of 500 nanometers is. I see the complete question.
I took a picture of my quiz. Do you want to see?
No.
We can still pull it up.
I fully believe you. I just wanted to make sure that I wasn't crazy. Because every time that I log in, I see this. It's there.
We are not crazy.
I'm not insane.
No.
No,
You're not insane.
No, you have your
Canvas is insane.
Canvas is insane. Okay, so it is up there. Without that number, yeah, you're not going to get the answer. Okay, somebody did comment on the quiz, and I guess they went through and kept solving the question, plugged in all the answers,
Yeah,
and found, okay, the slit width based on the correct answer is this, and sure enough, that's what it is. Okay, so yeah, I don't know what went wrong. I have no idea why that happened, but everybody's going to get credit for that question. Okay. That was technical difficulties, I guess. How would we actually do it, though? Let's make sure we know how to do it. Switch back to HDMI. Baby, come on. Come on. Come back. Come back. Come on. It's broken. Class canceled.
Test canceled.
All right, number 4. So how do we do this? We have the slit width. This is a single slit diffraction problem. 1.49 times 10 to the negative 6. Wavelength is 500 nanometers. And we are asked to find the second order minima. So I'm going to call it n equals 2. So this was another question that I actually happened to glance this morning, right? And I usually don't answer questions that were submitted in the mornings because I don't have time to. But I happened to glance this one and figured this is worth mentioning. So this is the difference between interference and diffraction. It's a different equation, technically. It's n times lambda equals a sine theta. That looks very similar to the interference equation m lambda equals d sine theta. So in interference, this equation, I think I mentioned this in the lecture, I hope I do. This equation predicts where bright spots are. So that gives you where the bright bands are. In diffraction, this equation, it doesn't give you bright spots. It gives you minima. It gives you dark spots. There's actually not a nice clean way to find out where all the bright spots are in diffraction. Single slit diffraction. Single slit diffraction tells you where the dark spots are. The equation is the same form, but it's giving you different things. Okay? So n is the order of the dark spot. So n equals 2 in this case. We're asked to find the angle, so in all the other problems we've done so far, theta is what? N times lambda divided by a. We want to do the inverse sign of all of that. N is the order, lambda is the wavelength, a is the slit width. Which apparently on a quiz you're not given, but on an exam you would be given it. If I didn't go to you on an exam, what would you do? I'll ask Evan. Okay? So you plug and chug your numbers in here, and you'll get a 42.2 degrees. If you got a super small number, what did you do? You're in radians. Okay? Questions on number 4. No? So those were all the questions that were submitted for chapter 34 at the time that I was making lecture. Okay?